Good afternoon, distinguished chairs, colleagues, and friends. My name is Zhao. Today, it is my great honor to present our work titled Effect of Precursor Composition and Oxide Ratios on the Performance of Geopolymer Mortar. My presentation is divided into 4 parts. Part 1. Introduction. Let's start with the global imperative. The production of ordinary Portland cement is a major contributor to co-emissions, accounting for about 8% of the global total. This urgent environmental challenge has accelerated the search for sustainable alternatives. Among them, geopolymers stand out. They are synthesized by activating aluminosilicate precursors, forming a robust 3D network. Their appeal lies not only in a reduced carbon footprint but also in their superior mechanical properties and durability compared to traditional cement. The performance of geopolymers is governed by their precursors such as fly ash, slag, and metakaolin. While binary systems like Slag-Fa or MkFa have been extensively studied, a critical question remains largely unanswered. Can a ternary system combining metakaolin, slag, and fly ash unlock superior synergistic performance? This gap is significant. A ternary system offers a more complex interplay of key oxides, silica, alumina, and calcium, which could be the key to ultra-high strength applications. Therefore, the primary objective of this work was to systematically evaluate this ternary synergy. Our specific aims were threefold. 1. To compare the performance of fly ash-based, binary, and ternary mortar. To link precursor composition directly to fresh and hardened properties. 3. And crucially, to identify the key oxide ratios that govern the development of ultra-high strength. Part 2. Experimental program. To achieve this, we designed a comprehensive experimental program. First, our materials. We used 3 core precursors: Class F fly ash, ground granulated blast furnace, slag, a rich source of calcium, and metakaolin, notable for its very high specific surface area and alumina content. They were activated by a 12 meters NO-HN sodium silicate solution. Our mix design was the heart of the study. We formulated 10 different mixes. This included a fly ash control binary series where Fa was partially replaced by either slag or metakaolin, and a ternary series where we incorporated all 3. For instance, F40G30M30 means 40% fly ash, 30% slag, and 30% metakaolin. All other parameters, like the activator-to-binder ratio, were kept constant. Regarding curing, we employed 2 regimes: standard ambient curing and a heat curing at 65 degrees Celsius for 12 hours to assess its impact. Finally, our test methods comprehensively evaluated fresh properties like flow and setting time, and hardened properties compressive and flexural strength at 7 and 28 days. Part 3. Results and discussion. Now, let's delve into the key results. I will start with the fresh properties, then move to the mechanical performance, and finally reveal the underlying chemical rule. For workability, for the slag series, the reduction is relatively modest, between 1.4 to 4.4%. We attribute this primarily to particle morphology. Fly ash particles are largely spherical, acting like miniature ball bearings that enhance flow. Slag particles are more irregular, disrupting this lubricating effect. The effect of metakaolin, however, is dramatic and severe reduction of up to 14.7%. This is not a morphology issue, but a surface area phenomenon. As you recall, metakaolin has a specific surface area of over 4,000 meters squared per kilogram, nearly 10 times that of fly ash. This vast surface area has a tremendous thirst for water. In a system with fixed water content, incorporating metakaolin effectively soaks up the free water needed for lubrication, drastically increasing the viscosity and reducing flow. This is a critical practical constraint for mix design with high metakaolin content. For setting time, the fly ash only mix ethanol did not set within 24 hours. This is a well-known challenge for low-calcium fly ash geopolymers at room temperature due to slow dissolution and polymerization kinetics. Introducing slag changes the game completely. As the slag content increases from 10% to 30%, both the initial and final setting times are dramatically shortened. This is because slag introduces soluble calcium ions into the alkaline solution. These Ca² ions rapidly participate in reactions, promoting the precipitation of early calcium-based gels like CSH, which effectively nucleates the solidification process. In stark contrast, the incorporation of metakaolin, even up to 30%, showed minimal influence on the setting time. Despite its high reactivity, metakaolin does not provide the same ionic driver calcium that catalyzes setting at low temperatures. This highlights a crucial, distinct role for slag. It is not just a strength contributor, but an essential component for achieving practical setting behavior in ambient cured systems. First, look at the binary systems. The impact of slag is nothing short of transformative. The pure fly ash mix, F100, developed only 3.3 megapascals at 7 days, with 30% slag, F70G30, the 7-day strength skyrocketed to 66.5 MPa, a 20-fold increase. The 28-day strength followed suit. This is the slag effect. Its high calcium content leads to the rapid formation of a dense, strong matrix rich in CISH gel. The binary story with metakaolin is more nuanced and frankly, puzzling at first glance. While a 10% replacement boosted strength, further increasing metakaolin to 30% resulted in a mix F70M30 that was actually weaker than the pure fly ash control. Why would a more reactive material yield worse results? We believe this is due to a combination of factors. The high water demand creating a more porous matrix, and a potential stoichiometric imbalance where excess alumina isn't efficiently incorporated into a strong gel network in this low calcium system. This sets the stage for our key finding. When we introduce metakaolin into the strong binary base of slag and fly ash, something remarkable happens. Instead of decreasing strength, it continuously enhances it. In the ternary series, as we replace Fa with Mk while holding slag constant, the 28-day strength climbs. The pinnacle is F40G30M30, achieving 121.2 megapascals. This is an 11.4% increase over the best binary mix. This is the unambiguous signature of ternary synergy. Metacolin's high alumina, which was detrimental in a local CM binary, becomes highly beneficial in the calcium-rich environment provided by slag. Heat curing at 65 degrees Celsius, as shown here, acts as a powerful accelerator. It particularly benefits the slower systems, like pure fly ash and fly ash metakaolin binaries, boosting their 7-day strength by 4 to 7 times. This is because heat energy overcomes the kinetic barriers to dissolution and reaction. However, and this is a critical insight, the effect of heat curing on the ultimate 28-day strength was relatively minor across all mixes. The ranking of mixes and the absolute peak performance remain largely unchanged. The ternary mix, F40G30M30, still achieved the highest strength of 123.6 MPa under heat cure. This tells us that while heat is a useful processing tool, the inherent chemical synergy between the precursors is the primary dictator of ultimate performance. The story for flexural strength is perfectly consistent. The trends mirror those of compressive strength. Ternary systems consistently outperform binaries, with F40G30M30 again leading the pack. This coherence between compressive and flexural behavior strengthens our confidence in the observed synergies, indicating a fundamental improvement in the microstructure and binding capacity of the mortar, not just a singular property enhancement. This leads us to our most profound finding, the oxide ratio golden window. Consider the starkest contrast in our study. F40G30M30, our champion at 121.2 MPa versus F70M30, the weakest at 28.8 MPa. A simple glance at their overall composition isn't enough. We need to look at the ratios. Their silicatal-amina ratios are quite similar, around 0.79 and 0.82. The decisive difference lies in the calcium to silica ratio. F4 OG30M30 has a Cal SEOs of 0.43, while F70M30 has a very low ratio of 0.11. This led us to a systematic analysis of all mixes. When we plotted performance against these ratios, a clear golden window emerged. We found that optimal 28-day compressive strengths exceeding 97.8 MPa and reaching up to 121.2 MPas were consistently achieved not by one ratio alone, but by a specific combination, a CO-Zalco ratio between 0.72 and 0.79, coupled with a Cal-SEOs ratio between 0.4 and 0.5. Why this window? It represents a state of chemical harmony. The silica-alumina ratio in this range is ideal for forming a well-connected, stable sodium aluminosilicate gel framework from the fly ash and metacolin. Simultaneously, the calcium-silica ratio in this range provides the optimal amount of calcium from the slag. This calcium doesn't interfere but integrates, promoting the formation of a dense, strong calcium aluminosilicate gel that coexists and interlaces with the unacid gel. This hybrid, interpenetrating network is the microstructural secret behind the ultra-high strength. Outside this window, you either have insufficient calcium for this synergy or an imbalance in the aluminosilicate network itself. Part 4. Conclusions. In conclusion, our study delivers 4 key messages. 1. For workability, metacolin severely reduces flow, while slag is crucial for achieving practical setting times. 2. For strength, slag is a primary driver. Metacolin alone in a fly ash system is suboptimal, but in a ternary system, it enables powerful synergy. 3. The optimal system is the ternary mix F40G30M30, which achieved a peak strength of 123.6 MPa under heat curing, demonstrating clear potential for ultra-high performance concrete. 4. Most importantly, we provide a rational design rule. The identified golden window of oxide ratios serves as a powerful guideline for engineering high performance, sustainable geopolymer concretes. This work provides a validated pathway towards next-generation, low-carbon construction materials. We are currently investigating the long-term durability of these ternary systems. Thank you for your kind attention.